so this is lecture 32B. This is basically part 2 of the previous video where we're going to be talking about the infinitesimal generator matrix. So what we had last time was we talked about this alarm clock and how we go from state I to state J, and that you had this alarm that would ring and it would basically tell you which state you were moving to based upon which alarm clock rings first, and then your state I would transition to whatever state would ring first. And so we had these transition rates Qij, and so from those we could get our holding time. Basically our holding time for state I was the sum of all of these transition rates. We could also get the probability that we're going to move from one state to another state. So basically our probability transition matrix for our embedded chain we could get by looking at which one's going to ring first. That would be this rate of our ij clock over the sum of all of our rates. Okay, so from here we can actually generate what's called the infinitesimal generator. So in continuous time, transition rates always play a fundamental role when working with Markov chains. So the derivative of a function describes its rate of change. So it's not surprising that the derivative of the transition function is also what is most important. Because we're talking about rate of change and when something is going to change. So we assume the transition function p of t is differentiable, and we're going to derive the infinitesimal generator matrix from this p of t. So if the process is last in state I before moving to some other state j that's not equal to I, then the instantaneous rate from state I to state j is given by our limit as delta t goes to 0, the probability that we go from state I to state j in this period of delta t divided by delta t. So this is our instantaneous rate of change from state I to state j, which is otherwise given as pji of delta t divided by delta t. So remember what we have, we can think about writing this more like something that looks like a derivative from Calculus 1 if we just remember that pji at time 0 is equal to 0 unless I is equal to j. So here if we're talking about I not equal to j, that's what we're talking about here, I not equal to j, then we can basically add 0 by, so this is 0, it just looks more like a derivative, right? And so now if we look at this, it really does look like a derivative, and it looks like just pij prime of 0. So it's the derivative here. So we're going to let q, which we're going to be, it's going to be our infinitesimal generator, is going to be p prime of 0. So if we think about the off-diagonal elements of our Q matrix, basically j not equal to I, then all of our off-diagonals are simply defined as those rates of change from I to j, or qji, that we talked about previously. So all of our off-diagonal elements are the same as what we talked about before. So the question is what is our diagonal elements for this infinitesimal generator matrix Q? So this is going to be a matrix in which the off-diagonals gives us our transition rates, but we need to figure out what happens when I is equal to j. So when I is equal to j, we have qii is defined to be, so we're looking at p prime of 0, so here this is going to be pii of delta t minus pii of 0 over delta t, so just our derivative. Pii now at 0 is just 1, so here we have pii of delta t minus 1 divided by delta t. But we know that if we sum up p going from the probability of going from I to j for all of our states, it has to equal 1. So we can simply write 1 minus pii of delta t, so think about the negative of this thing, is just the sum of all of our entries, just j not equal to I. So we basically take our ith entry and we move it to this side, and we keep all the rest over here. So we're gonna, so what we have now is we have basically the minus of that thing. So since qij is this limit of Pij of delta t divided by delta t, then we have that Pij of delta t is Qij times delta t plus some order of delta t. So what we're going to do is we're going to put that in. So we have 1 minus Pii of delta t is the sum of all these. We're just going to replace that Pij of delta t where we have these Q values in here. So we have these transition rates that we talked about before. So now what we can say is that our Qii, our diagonal elements, are simply minus the sum, as j goes from 0 to infinity, just j not equal to I, of all of these transition rates. So remember how we can write this. We can think about this being, we can take the sum out because the limit of a sum is the sum of the limits, right? So we can bring this sum out and we can look at the limit of Qij delta t over delta t. And we have the limit of order of delta t over delta t. Remember, this thing always goes to 0. Here the delta t's cancel out. So the limit of a constant is just a constant. So we just have minus the sum, j goes from 0, not equal to I, to infinity of Qij. So think about what this is. This is just our parameter for our holding time in state I. So this is minus Qi. So we have the sum as j goes from 1 to infinity of Qij is simply going to be equal to 0. The Q matrix is called our infinitesimal generator matrix, or simply generator. And it's the most important matrix that we have for continuous time Markov chains. So here we derived Q from the transition function P of t, but normally whenever you're doing any kind of modeling, Q is the one that is actually we know first. So we normally identify transition rates based upon some kind of information that we're given by the system, some type of qualitative or quantitative dynamics of what's supposed to happen. So normally your mathematicians tend to talk to biologists or physicists, somebody who knows more about the rates at which something is going to happen. So you normally talk about the rates first, and then from these rates you actually get the transition function and holding times, etc. So notice that the generator matrix is not a stochastic matrix. So we have negative diagonal elements, we have entries that can be greater than 1, and we have columns that sum to 0. So the next time we're going to actually talk about kind of the way we actually do things. So we actually think about what is the generator matrix first, Q first, and then how from this generation matrix we can actually get this transition function P of t.